as we continue our discussion of angle identities, we have added two more groups of identities to our list here. The first set are the double angle identities. And there is a lot of them because cosine actually has three different versions depending on what you have and depending on what you know. So the cosine of a double angle could be cosine squared minus sine squared. It could be 2 cosine squared minus 1, or it could be 1 minus 2 sine squared. The differences between these is because of the Pythagorean identity and being able to manipulate those a little bit. If you want the sine of a double angle, it's only got one version. And if you want the tangent of a double angle, it only has one version. In a standard form here, tangent does things a little differently. It has a fraction, the other ones do not. The other one we're studying today is the half angle identities. Now for the half angle identities, something where we take an angle and cut it in half to get the value we want. We've got a sine version where it's 1 minus the cosine over 2. We have a cosine version where it's 1 plus the cosine of a over 2. So these are very similar. The sine is minus, the cosine is plus, which means we need to know the cosine value in order to do either one of these. The tangent, again, being a little different, we have 1 minus the cosine of a over 1 plus the cosine of a. So it uses a little of both, which makes sense because tangent is sine over cosine. I've got the 1 minus on top, the 1 plus on the bottom. The 2's are going to cancel out. The other unique feature about these half angle identities is the plus minus that's out in front. That does not mean there's two answers. That plus minus, that particular one, we choose either positive or negative depending on the quadrant of the angle we're looking for. So for instance, if I was taking a 30-degree angle and cutting it in half, I know I'm going to land in the first quadrant. I know sine is positive in the first quadrant. I would choose the positive one. But if I took something in the fourth quadrant and cut it in half, I'm going to land in the second or third. So now I know that cosine would be negative, sine would be positive. So it depends on which quadrant your resultant angle ends up in. So let's take a look at some examples that use the half angle and the double angle identities. Now, much like the cofunction, the negative angle identities, the sum, and the difference angle identities, we have various things that we can do with our half angles and our double angles. We're going to revisit the verify again, and you'll see that we have a double angle right in here. But because there's so many versions for the cosine of a double angle, I'm going to take a peek, and I notice that they stick with cosine. So I'm going to do the same. I'm going to stick with cosine, and so I'm going to use the second version of the double angle formula. I've got the 2 out in front. I'm going to replace the cosine of 2 theta with 2 cosine squared theta minus 1. Now if I distribute that 2 in, 2 goes in here, I get 4 cosine squared of theta minus 2, and I'm already the same as the other side. So I used a certain version of that double angle. It just depended on what I needed. In this case, I needed to stick with cosines. For this one right here, I realized that 120 degrees is on my unit circle. So I would never necessarily use a double angle formula if it's one that I already know. But just to walk you through the process of how these double angle formulas work, I'm going to rewrite this as the cosine of 2 times 60. 60 being a first quadrant angle, one that I use all the time. So if I use the double angle formula, and it doesn't matter which version I use, but I'm just going to use the first version. The first version says cosine squared of the angle minus sine squared of the angle. And the angle in this case is 60 degrees. So I need to take the cosine of 60 degrees, which is 1/2, and I need to square it. Then I need to take the sine of 60 degrees, which is the square root of 3 over 2, and square it, and then subtract those two things. So the arithmetic on these is not real strenuous. Go ahead and square this out, 1/4. Square this out, I get 3/4. When I take 1/4 minus 3/4, I get -2/4 or -1/2. I think it's a whole lot easier to go to negative or go to 120. Look at the cosine value and you'll see that it's -1/2. But those double angles are there to use if we need them. For the sine of 15, in the last unit, we did a sum, or in this case, a difference identity to get to 15. But let me show you another way of getting there. The sine of 15 is the same as writing the sine of 30 cut in half. So 30 is my angle that I'm going to deal with, and 30 is on my unit circle. Now, the half angle formula for sine says I'm going to either go positive or negative, and I'm going to take 1 minus the cosine of the angle, and then divide that by 2. Now, I'm going to go ahead and pick my sine. I started in the first quadrant. When I cut that in half, I'm still in the first quadrant. Sine is positive in the first quadrant. That's how I pick my sine. So this is definitely going to be a positive answer. So I need to know what the cosine of 30 degrees is. Well, the cosine of 30 degrees is square root of 3 over 2. So that's what I'm going to use, is square root of 3 over 2. Sine of 15 degrees is 1 minus the square root of 3 over 2 all over 2. Yeah, there's a little work to do here. Little simplifying because all of this is underneath my radical. So I get a common denominator here. 2 over 2 minus the square root of 3 over 2. I can put those together now. And I can get 2 minus the square root of 3 over 2. That's all supposed to be divided by 2. So I have a fraction divided by a fraction. I keep it, change it, flip it. And I get the 2 to go on the bottom. I get something like 2 minus the square root of 3 all over 4. And that's supposed to be square rooted. Now, I could put that square root in. I could square root the 4. But this is simplified enough for our purposes. That's what the sine of 15 degrees is. That's the answer that we're looking for that particular one. What I want to really get into, the heart of what I want to get into, is these types of problems where we actually have to do a little problem solving to figure this out. So there's a lot to take in here. They gave me a sine value. They gave me what quadrant we're in, and they told me what we're trying to find. But they never told me the angle, and that's okay. They're not trying to find the actual angle. They're trying to find what the sine of that half angle is. So I'm going to start out by using this. If I go third quadrant and I try to draw in a sine, I'm going to actually draw in this part right here. If this angle is sitting here and it says the sine is -24/25, sine is opposite over hypotenuse. So I can find that missing side by using the Pythagorean theorem because this is a right triangle. So a squared, what we're trying to find, plus b squared equals c squared. And if I solve this out, I end up getting a squared is 49. Square root of 49 is 7. So I now know that this missing side over here is 7. It actually is a Pythagorean triple. I now have everything I need in order to do this particular calculation. If I look at my half angle identity, the sine of theta over 2 is defined as being positive or negative square root of 1 minus the cosine of our angle divided by 2. I don't need to know the angle. I just need to know the cosine value. So now that I have this right triangle and I know everything, cosine of this angle is adjacent over hypotenuse. So the number that goes right in here is 7/25. Okay, I figured all that out. I never needed to know the angle. And that's the hardest part with these types of problems. Everybody tries to find the angle first. I could figure out what that angle is, but I don't need it in order to figure this out. Now there's definitely some simplifying to do here. I'm going to rewrite this as 25 over 25 minus 7 over 25. That gives me 18 over 25. And I have a fraction divided by a fraction, so I'm going to keep it, change it, flip it. I end up with 18 over 50. I got to keep that square root in there. And I have to figure out where this is. Now, we started in the third quadrant. So if I cut this in half, I'm talking 90, and I'm talking 135. That means I'm somewhere in the second quadrant, and I know that sine is positive in the second quadrant, so I'm going to take the positive form of this. Now, we can definitely do some simplifying. I can get an answer here. If I take 18 and 50 and I take out the 2, then I get 9/25. When I square the 9/25, I'm going to get a 3/5 as a final answer. So I should probably do a little arithmetic there and simplify my radical. But I got this cosine value right here based off of the triangle. That came from that information, and I drew it in the third quadrant based on this information. I'm trying to find the sine of the angle, cut in half. I do not need to know the angle. You can, it's not necessary. It doesn't change anything that we did here. Another example, I did a tangent one, okay? One that's very similar to it, but again, when we talk about the half angle formulas, the half angle identities, they all have to do with cosine. So I really need to get cosine out of this example. This again tells me we're in the third quadrant. So when I draw, I'm going to draw a third quadrant. And it tells me what tangent is. So if I draw in this right triangle, tangent is opposite over adjacent. So I'm missing my hypotenuse. And I need that because cosine uses hypotenuse. So a squared plus b squared equals c squared in this case. So 4 plus 9, c squared is 13. So c is the square root of 13. Now I'm going to use the half angle formula, or excuse me, a double angle formula for cosine. This one's asking for a double angle. It doesn't matter which version you use. There's 3 versions for cosine. I think this time I'll use the second version, which looks like this. That's the double angle formula for cosine. The cosine angle in this particular case, 2 over the square root of 13. So I've got this 2. I've got 2 over the square root of 13, but I'm supposed to square that and then subtract 1. And that's supposed to be my double angle. Squaring this on top gives me a 4, and the 4 times 2 gives me 8. Squaring the square root on the bottom makes that really easy. I'm going to convert 1 so it has a common denominator. 13 over 13 is just 1. 8 minus 13, that gives me a negative 5/13. And that's what the cosine of the double angle would end up being for this one. Again, I never needed to know the angle. We never did an inverse tangent or an inverse cosine or anything like that on either of these problems to find out the angle. The angle, or excuse me, what they gave me with the angle was to help me draw the triangle so I could pull out cosine values, sine values, or tangent values.